Okay, so even answers. We did some more problems because this whole logarithm thing is new. So let's see. Oh, 28 I was supposed to graph. Okay, well, I'm not going to record that. I'll come back. Okay, so here's 28 graph. The starting point was 0, 3. The asymptote moved left 1, negative 1. We're talking about 34 now, and we need two things to graph this. We need the asymptote, which is the parentheses part equals 0, and you solve it. Okay, so that is the value. It can't be 0. You're not allowed for this to be 0 because there's no way to get 0 no matter what exponent you use. So that's where the asymptote comes into play. And then usually the starting point is at 1, 0. So not this time, but usually. So if you can figure out what moves, this is going to be left 3, and this is going to be up 4, right? Because those two translations, which means if you graph it, then you're going to go from the usual starting point, which is at 1, 0, and you're going to count left 3, 1, 2, 3. That's that negative 2 that you found. That's what makes this value 1. That's the special exponent we have as 0. And then up 4. So it's here. So these are just dots to help me get there. They're not real dots. So this was my new starting point. If you do this, and you know where you normally start from, you can count over and find it. And then the asymptote was at negative 3, so that's at negative 3 right beside it. And then it flips over. So just like this one flipped over, normally a logarithm starts at the bottom and goes up. This one has a flip to it, so it goes like this. So it had a flip. Say again? This negative. So let's try a point. If we know that the starting point is negative 2, let's try negative 1. So that would be 4 minus log base 10. Negative 1 is going to be hard. So we're not going to be able to figure that out really well. Let's try something else. Remember how we thought about this smart like? How could we make this part 10? 7. So let's try 7. Okay, so 7. Now we've got 4 minus log base 10 of 10. What exponent do you give 10 to be 10? So this whole thing can be replaced with 1 because that's the exponent. So at 10, I'm sorry, I lied. We plugged in 7, right? At 7, we get this. 4 minus 1 is 3. So when we go out to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it's only at 3. It really has a long stretch to it. It's better than mine when we have a better point. That 10 is what made it stretch out this far. But then when we use small numbers, we get, when we use like little bitty numbers here, we get fractions for this part. Like if we use 3.5 or negative 2.5, look at that. 4 minus log base 10 of negative 2.5 plus 3. This isn't going to work exactly, but it will give us an idea of the value. That means 4 minus log base 10 of 1/2. And how do you make a fraction? It's not this fraction, but how do you make a fraction? You would use a negative number. So this is going to be some negative number. 4 minus a negative number is going to be what? 4 minus a negative number is going to be 4 plus a number. It's going to go up. So what we want to do is we want to be able to pick out all the translations and think about what it should look like and move it. So let's look at 40. 40 is pretty straightforward. It doesn't have as many things. It says log base 2 of x minus 3. So when you see log, this is what I want you to think. Normally it looks like this. I want you to be able to picture log in your head so that when you look at this one and do the translation, which is right 3, opposite math, write 3. Then all you do is take this whole graph and you go 1, 2, 3 and put it here. So if you know what the parent function looks like, you can move it. And then I forgot 42. So I don't know what number that was. 40 went with F, like Frank. And then what did I say, 42? So 42 says log, it doesn't, it says minus log base 2 of x. So this is the only thing that's different. And the negative in the front means vertical flip. So we're going to take our normal graph, which goes to this point, follows the asymptote and goes like this. That's the normal graph. And we're going to take this part and put it on the bottom. We're going to take this part and put it on the top. And that's our graph. That's a quick sketch of it, at least. It didn't have any left-right shift. Okay. 66 through, so these were working out numbers. So here you go. Oh, it started with 56, didn't it? 56 is 1 when you're checking your work. 58 is 1/5. 60 is 2. 62 is 64. 64, well, that's convenient. They've been matching up. 64 is 1/8. Oh, I lied. 64 is 9. 66, negative 1/2. So these were the evaluation ones. Are there any of these that you want to go over? 66, let's go. Okay, so this one has a lot of layers, but we're going to think about the inverse part of this. 66 says log base 3 of 9 to the 2x equals negative 2. So it's got too many layers. It has a base and another base and then an exponent. It's just like way too much stuff. So could we rewrite 9 as the same base that we have down here so that our bases are the same? Could we make 9 into something else that equals it? What could we say? 3 squared, right? So if this is 3 squared, I'm just replacing 9 with 3 squared to the 2x. Then this is helpful if I do this, which is log base 3 of 3. And then this rule is that you multiply them when you have one base and 2 exponents. You multiply them and get 4x. So now we know this has a base of 3 and this has a base of 3. They cancel each other out. They're inverse functions. And now we say 4x equals negative 2 divided by 4. X equals negative 1/2. So what is this? This is all about finding the same base. We're going to do that over and over again. And then if we know we have the same base, we can figure out what the function does and try to evaluate from there. So we have to be really good about our rules, though, because if we did this part wrong, we wouldn't be able to get to the end. But one base to 2 exponents means you multiply them. Any other ones? 61. All right, Diggs, have a great spring break. 61, I guess we did the other day, but it's good to go over now. Log base 16 of x equals 3/4. Thank you. This is a different kind of problem. And maybe one of the hardest parts about this section is that they're presented in different ways. And with practice, you figure out how to do it. But I can't do this like the last problem. I can't make x into a base of 16. So instead, I need to consider that this is a base of 16. And the whole purpose of logarithms is that this is an exponent. So we need to, and even though it's not a verb, but I'm using it as a verb, we need a hamburger helper it. We need to take the 16 and use this as the exponent and then say equals x. So 16 to the 3/4 equals x. This is the base. Logarithms are exponents, so this is the exponent. And then the argument is the result of those two things put together. Now you have this. You can think of it as the fourth root of 16, all cubed. And 16 does have a fourth root. What number times itself 4 times makes 16? Not 4. What number? 2. So this part is 2 cubed equals x. So x equals 8. And they're different kind of problems. You have to figure out how to simplify. And sometimes you might need to try something, and then if it doesn't work, try something else. But what we're trying to do is just get enough practice that we have some things to try. So don't give up. Just try something. So this time, we were trying to get the exponent down. So we were trying to get rid of the logarithm. This time, we didn't have x in an exponent position, so we had to rewrite it so that we could use the exponent. Just different kind of problems. Other questions that you would like to see done? All right, you guys at home, if there's some that you needed, email me, and we can start on Monday when we get back with those questions as a review to warm up before we keep going. All right, happy spring break.